This conference will now be recorded.
All right, we're set. I turn it over to Ryan.
All right. Hey, everyone. Thanks for showing up. So this is lecture 5, and we're going to talk about convolutional neural networks and interpretation of convolutional neural nets, or I'm just going to say CNN from now on. So just to refresh everyone's memory, in lecture 4, we were talking about fully connected neural networks, which are the traditional kind of neural networks that have been around for quite a long time, since the 1960s, I think. And those types of neural networks are completely spatially agnostic, or basically if you have any topological relationships in the input data, so if the input data are on a spatial grid or a temporal grid or both, a fully connected neural net can't handle those relationships. So it can still use the data that come from a spatial grid or a time series or what have you, but it can't identify spatial or temporal relationships. It treats all the predictor variables as independent scalars, but CNNs can learn relationships in space and time. So that's the main difference between the two types of neural networks. So I'll start off with an overview. We're going to cover convolutional neural networks, CNNs. That's where we're going to spend most of our time today. And then I'm going to talk about 4 different interpretation methods at the end of the lecture. So the first one will be the permutation importance test, and the second one will be saliency maps. You saw those already last week in lecture 4 for fully connected neural nets, but for CNNs, they work a little bit differently. And actually, I find that the output from those 2 interpretation methods is more interpretable when you're using CNNs than fully connected nets. And then we're going to talk about class activation maps and backwards optimization, which are 2 other interpretation methods that you can apply to CNNs. And there will be a CoLab notebook at the end of today. So I'm going to start. I'm going to start off by describing why the advantages of CNNs. So why it's often good to use CNNs instead of a fully connected neural network. And then we're going to talk about the different components of CNNs and really break it down and hopefully give you somewhat of an understanding of what's going on under the hood. So like I said earlier, CNNs are a type of neural network that's designed to learn from gridded data. That gridded data can be spatial and or temporal. So you can have spatial grids, you can have time series, or you can have time series of spatial grids. So you can have spatiotemporal data. Because CNNs can learn from gridded data, and because they often contain many layers, they're considered a type of deep learning. So in traditional machine learning, when I say traditional machine learning, I mean linear regression, log regression, decision trees, fully connected neural nets, etc. In traditional ML, the model has to be trained with scalar features, and those scalar features are created by pre-processing the gridded data. So if you have gridded data and you want to use traditional machine learning, you generally don't feed the full grid into a traditional machine learning algorithm. Instead, you compute scalars, you turn the gridded data into a bunch of scalar features, and then those scalar features become your predictor variables. So for traditional machine learning, the model is never actually seeing gridded data. So some examples of scalar features that you might pre-process gridded data into are principal components, summary statistics. You've seen those in the CoLab notebooks for lectures 1 to 4. So there's those 41 predictor variables that describe each storm, and those 41 predictor variables are created by pre-processing gridded data. So the actual gridded data that we get for each storm are a 32 by 32 grid of temperature, reflectivity, U wind, and V wind. And then the predictors in lectures 1 to 4 ended up being things like the maximum reflectivity inside the storm, the minimum temperature inside the storm, the standard deviation of U wind inside the storm, et cetera, et cetera. So those were summary statistics. Another thing you can do for scalar features is you could just feed raw grid point values into a traditional machine learning model. So if you have gridded data, you can just vectorize that. You can flatten it all into a one-dimensional vector and feed that full one-dimensional vector into your traditional machine learning model. But the problem is the traditional machine learning model still won't be able to reason about spatial or temporal relationships because it'll treat each element of that vector as being an independent thing. So because the creation of scalar features is done as a pre-processing step before machine learning, when you're doing traditional machine learning, it doesn't optimally exploit the spatial or temporal structure that's in your data. Usually you can do better. So what's nice about CNNs is they simultaneously learn 2 different transformations. They learn the transformation of gridded data into scalar features. They do that with spatially aware layers that do convolution and pooling, which you're going to find out about soon. And the second transformation CNNs learn is going from the scalar features to the predictions. And CNNs do that with fully connected layers, which are the same as the layers you see in a fully connected neural net. So you can think of a CNN as being a spatiotemporal feature extractor concatenated to a fully connected neural network at the end. And you can see that in this image at the bottom, where the convolutional and pooling layers are the spatiotemporal feature extractors. In this case, they're only spatial because we don't have temporal data. We just have one picture, in this case, of a bird. So the convolutional and pooling layers are extracting spatial features from this this grid or this image, and then we vectorize everything. So we take all the features that have been detected by the convolutional and pooling layers, flatten them into a one-dimensional vector, and then feed them through some number of fully connected layers. And the final output is a whole bunch of class probabilities. So in this case, the CNN can detect birds, sunsets, dogs, cats, etc., and it outputs one probability for each category. So learning directly from gridded data generally improves skill, so it makes the predictions better. We've seen that with many applications in recent years. There's way too many to create an exhaustive list. I'd probably take up all 50 slides just creating a list of all the applications that CNNs have done really well on recently. But a few examples are image classification. So CNNs are really good at identifying dogs, cats, birds, even identifying the breed of a dog or a cat. CNNs are good at facial recognition, disease diagnosis, galaxy classification. I don't know if anyone remembers the Galaxy Zoo website from about 10 years ago, where they were getting basically citizen scientists, like any member of the public could go online and you take this quick 5 or 10 minute tutorial on how to label galaxies as being globular clusters or spiral galaxies or disk galaxies or whatever. And then you go through a bunch of images and label them. The reason they were collecting all these labels is they were training a machine learning algorithm, which ended up being a CNN, and the CNN ended up doing really spectacularly well. There's a paper out on that from 2015, I think. They were classifying galaxies into 10 different categories, and they ended up with an accuracy of 99.8% or something. Another kind of a less benign application of CNNs is deep fakes. So if anyone's seen those videos where Obama is giving a speech, but someone has put other words into his mouth, so it's a speech that he never actually gave. Someone has just put the they've fed the audio track into a CNN, and then they've gotten the CNN to animate Obama's face and make him speak these words, but he never actually said those words. So that's another thing that CNNs can do, which unfortunately is not as beneficial. Imme?
Could I add one thing? Yes, you were mentioning before that they had this Galaxy crowdsourcing example, and people are doing very similar things right now for atmospheric rivers and the like. So that's an effort of LBNL, Lawrence Berkeley National Laboratory, where they have lots and lots of atmospheric scientists at conferences and other places just label what is an atmospheric river and what isn't. Or I think they do it with hurricanes as well and a few other things, and then they try to then train a neural network based on those labels.
Yeah, thanks for bringing that up. The name of that effort is either ClimateNet or EnviroNet. I can't remember, but if you...
It's ClimateNet. It's ClimateNet.
It's ClimateNet these days? Okay,
yeah.
So there you go. So another good thing about learning from gridded data, it not only improves predictions, but it often improves interpretability as well, because for many interpretation methods, the output of the interpretation method is a map that has the same dimensions as the input or predictors. So if your predictors are just a bunch of scalar things, like we had in lectures 1 to 4, you can't really create a gridded map. You can't create an image as the output of an interpretation method. But here, where we're training CNNs with images, if the input is an image and then the output of the interpretation method is in the same space as the input, you can look at your interpretation maps as an image. And a picture is worth 1,000 words, as some people say. I find that people in general, but especially meteorologists, are used to looking at gridded data and often get more out of looking at gridded data. And in addition to all this, CNNs are rapidly gaining popularity in atmospheric science and geoscience in general. And if you want a whole bunch of examples, you can just look at the abstracts from AMS 2020 and AMS 2021 in the Artificial Intelligence Conference to see how many people are doing CNNs these days. So now we'll go into the components of CNNs. So we're going to talk about their inner workings for a little bit. So CNNs are made up of 3 different components. There's three main types of layers that go into a CNN. And at the end of all this, I'm going to talk about convolutional layers, and then I'll talk about how pooling layers work, and then I'll talk about how fully connected layers work, which won't take long because you learned about that in lecture 4. And then I'll show some pictures with the architecture of CNNs to show you how everything goes together, so how we string together the convolution and pooling and fully connected layers. So the first main component is convolutional layers. These are made up of convolutional filters, and those convolutional filters detect topological features. And when I say topological, I mean spatial and/or temporal. Convolutional filters are nothing fancy. They've actually been used in image processing for decades to do things like blurring, sharpening, edge detection, etc. So if you've ever used Adobe Photoshop or GIMP or any of that other photo editing software, when you apply a blurring filter or a sharpening filter, for example, that's almost always a convolutional filter. The difference is that in those traditional applications like photo editing, the weights inside the filter are fixed, whereas in a CNN, the weights inside the filter are learned. This animation on the right-hand side is showing you what a convolutional filter does. So the part of the image that's highlighted in yellow is the convolutional filter. So we have a 3x3 filter stepping over a 5x5 image, and then the output after you've done applying the filter to the image is a 3x3 image because it cuts off the edges. There's different ways that you can deal with the edges when you do convolution, but in this case, the convolutional filter, it only goes to places inside the image where you can completely fill that 3x3 grid with input values, and then the red values inside the filter where you see ×1, ×0, ×1, ×0, etc. Those are the filter weights, which in this case are definitely not learned. They're just preset to be good for doing edge detection, but in a CNN, you actually learn those weights. So the second main component of CNNs is pooling layers. What pooling layers do is they just downsample the grid to a lower resolution, so they have no weights. There's nothing inside a pooling layer that's learned. A pooling layer just does one of two different kinds of pooling. So you can do maximum pooling or you can do average pooling. In the animation I'm showing on the right-hand side, the filter is doing maximum pooling. So at each location of the filter in the input grid, it just takes the maximum value and then puts that into the output grid. So for the top left, you get an 8. For the top right, you get a 6. For the bottom left, you get a 9. And for the bottom right, you get a 9. But you could also do average pooling, where you average all the 4 values inside that window rather than taking the maximum. In practice, I've found that maximum pooling and average pooling work about equally as well. Although maximum pooling is allegedly better for doing edge detection. So if you have a really simple problem where you just need to find edges in an image, you probably want to use maximum pooling rather than average. So the whole point of doing pooling is that shallow convolutional layers that come before a whole bunch of pooling operations have been done are able to learn small scale features because they're seeing the gridded input data at full resolution. And then deeper convolutional layers that come after you've done a bunch of pooling operations are seeing grids that have been coarsened by pooling. So the deeper convolutional layers can learn large scale features. And in a lot of different problem domains, especially atmospheric science, multi-scale data is important. So often, if you want to predict something, you care about processes happening at small scales, but you also care about processes happening at large scales. So doing pooling gives different convolutional layers a chance to learn features at different scales. And finally, the third main component of CNNs is fully connected layers, or sometimes we'll call them dense layers. I don't like throwing a whole bunch of different sets of terminology at people, but in machine learning literature, when people talk about CNNs, almost everyone calls these dense layers instead of fully connected layers. But they're the same thing as what you saw in lecture 4, where we're using fully connected neural nets. So these are the types of layers that go into fully connected neural nets that are completely spatially agnostic. So they have no way of dealing with spatial structure or temporal structure for that matter. And the job of these fully connected layers is that they take the features detected by the convolutional and pooling layers and transform those features into a final prediction, or in the case of the image I'm showing at the bottom here, a set of final predictions, because because this one does multi-class classification and not binary. And now I'll turn it over to Imme, and you're going to share your screen, right? Oh, maybe Imme's not here. Aha.
Okay, so I hope you can see my full screen now. Okay. Can you?
I see it.
Okay, good. So I just need the mouse. That's why for my slides, that's why we switched over. So what you've seen so far is mainly type 1 of CNN. So there are two primary types of convolutional neural networks. And so the first type that became really popular is the one that Ryan just showed you, the architecture, which has at least one fully connected layer at the end. So you have some convolution and pooling layers at the beginning, and then you have some dense layers here. And then the output is usually one or more scalars. And the scalars can be continuous, they can be discrete, or whatever you want them to be. But it's usually just scalars, it's not an image or something like this. And these kind of networks are great for recognizing objects in an image, recognize whether there's a tropical cyclone, convection, etc. And we're going to today only discuss those. But I want to give you a heads up also of type 2, which we're going to discuss a little bit more next time, because people ask for units and GANs, and they're going to fall into this category. And they are more image to image sensation. So here the input is an image, but the output may also be an image. But it usually is an image. And they don't contain a fully connected layer anyway, because once you have a fully connected layer, it's very hard to go back to an image, right? So because of that, you would only have our convolution layer, pooling layers, upsampling layers, which we do next time, and more pooling layers, and the output is an image. And again, those are good for image to image sensation. We use them, for example, for generating synthetic radar images from ghost imagery. And some of the names of those types of networks, depending on what architecture you're using, you can call them encoder-decoder networks. That's pretty much what's shown over here. Units, and they are also part of GANs quite often. And we'll discuss those next week. All right. So I wanted to revisit convolutional layers a little bit more, because there are a few more nuances that are really hard to get at the beginning. And I just want to make sure everybody gets those. So here's this wonderful animation that Ryan showed you. And this shows you what happens if you have one channel here, one image, and one filter. But usually you have several channels. You may have seen images of neural networks that have several channels throughout usually. So what if there's several input channels? So let's say, this is a typical computer science example. You have red, green, and blue for your 3 different color channels, and you're feeding your image with those 3 channels in. So how is convolution defined then? Well, it's pretty much first defined for each one separately. So you have one filter for red, one filter for green, one filter for blue, and they're all independent. So their weights are all learned by the neural network, but they're not the same weights. And so what you're doing then is you're going to apply those 3 filters, each one to one image. Each one gives you then for each point. So if you're trying to figure out what this number should be, you apply the red filter here to the red image. You get one number out of that for that pixel, which is 308 in this case. You do the same thing for the green, the same thing for the blue. You add those 3 numbers, and then you add the bias, and then you get, in this case, minus 25, which is now going to be this value. Okay, so they're all basically, you have 3 different filters that are all learned, but they're all applied at the same time, and the results are added for each pixel with the bias, and then you get the number. If you want to look at this more holistically, you could say, okay, I'm taking my 3 channels here, and I'm now making basically a 3-dimensional image out of that. So the depth here is just red, green, and blue channels, and you have your image here, and then your filter really becomes one filter that's 3-dimensional. So in this case, 3 by 3 by 3. This happens to be 3 because we happen to have 3 input channels. Otherwise, it could be 3 by 3 by 6 if you had 6 input channels. So you can now look at this filter as being one block where each number again is chosen. So the 3 filters can be seen as a single 3D filter. A single multi-channel feature comes out of it. And what the other point I wanted to make is that this is now a 3 by 3 times the number of incoming channels. But people only speak of a 3 by 3 filter because the channels are always implied. So when you hear 3 by 3 filter, it's really a 3 by 3 times the number of incoming channels, whatever that is at that layer of your network. So if you see 3 by 3, just realize that's what it means. Okay. So again, showing you the same picture as before. This is how you apply your filter. The number comes out, but notice one thing. We fed in 3 channels, but out comes only 1. So our red, green, blue images at the first input layer have now, by one convolution filter, been collapsed to a single channel. So it all collapsed to one single channel. It's now all smushed together into one type of feature map. But the thing is that quite often neural networks, I'm sure you've seen that there are often several channels even after the first layer. So the question is, where do the other channels come from? So again, here's just the image. You feed in your thing. you get a single channel out. So you only have a single channel left. But where do the other channels coming from? Where are they coming from? Well, you usually want to detect more than one feature, more than one pattern. So you don't just have one filter, you have several. So you use several filters at each convolution layer to look for several different patterns. Each filter looks for one pattern. So each of those cubes now looks for one type of pattern. And each feature creates a separate output channel of that layer. So the number of channels at the output is a number of different features or filters you put in. So the number of different patterns you recognized. I should say the number of different features you chose for that layer. So if you use 32 filters, you get 32 channels at the output. 32 maps to indicate the presence of 32 different patterns. And remember, these are new channels. They're not the channels of the prior layer. So your red, green, and blue in the previous example have collapsed, they're gone. Now these are all abstract patterns. And to give you a little bit more insight into this, the next thing I'm going to look at is a little bit of visualizing the filters and activations. That at least helped me a lot. But when I did convolutional neural networks first, it really helped me to visualize the intermediate results so that I could really see what the neural network was doing. So what you can visualize easily are the filters and the biases. So once the neural network has been trained, all the filters and biases are fixed. So for your neural network, you can just visualize all the filters and biases for each layer separately. That doesn't always tell us much. Sometimes it's very helpful. Sometimes I just find, oh, some of those filters are blank, which means I'm really having too many different filters because they're not even being trained. So then I reduce my number of filters, for example. But in most cases, this is more education. It doesn't tell you much about your system. You'll see an example why it doesn't help you very much. What's more interesting is to visualize the neuron activations. And they are only defined for a specific sample, because remember, you feed in one sample, and then you get those neuron activations throughout. Once your neural network is trained, you just propagate it forward from layer to layer, but at each layer, at the output, you can look at what those are. And so again, you feed a sample in the network and you watch how it's being transferred from layer to layer, and you visualize your neuron activation at each layer. I also hate to throw out lots of acronyms, but unfortunately, this has many, many different names, these intermediate activation patterns. Some papers call them neuron activations, some call them feature maps, some call them layer output, and some call them output channels. So any of those things mean the same thing. But let me give you an example. So this is an early example of the Gremlin model that Kyle and I trained to generate synthetic radar imagery from ghost imagery. And here you just see the very first convolutional layer. And remember, the parameters to be learned are the filters, which are in red and blue. All this colorful stuff are parameters that are being learned. The biases are not shown. That would just be one square for each little filter with one color. And then you see the neuron activations at the input channel here in gray. So in this case, because it's the first convolutional filter, these are actually physically meaningful things because these are the ghost channels. In this case, channel 7, 9, 13, and the GLM channel. And I apologize, the y-axis is upside down in these images, but never mind. These are your input images from ghosts. And now you feed them through your first convolution layer. And what that means is you apply this filter to this image. You apply this filter to this image, this filter to this image, this filter to this image. You add the results, you add the bias, and then you get the output of channel 1. So channel 1, again, here is now something much more abstract. It doesn't have a strict physical variable meaning anymore. It's now something, this is the feature you're looking for described by this filter. And this map tells you where in this original sample, this specific pattern is present. So for each pixel, it tells you where was this filter, how strongly was it represented over here. Again, imagine these filters being small and being overlaid over here. And then you get the second image out here, a second channel for the second filter, and for the third filter, and for the fourth filter. And I just happened to choose 4 filters here. There could have been 8, as there will actually be in the next example. But my key point is, this is the first layer of the network, which means the input channels now really mean something that is very clear because you know exactly what it is. But these are the hidden neuron activation patterns. You don't really know what they mean. Sometimes you can kind of figure it out by looking at a lot of samples, but it's not necessarily a priori clear what these mean, okay? And again, the only things learned are those filters and the bias weights, and everything else now just depends on the image that I'm feeding through. Let's go to the second layer. So we're taking now the output from over here, from the first convolution layer, and we're feeding it into the second convolution layer. So you find them over here. They already have an abstract meaning here because again, that's the output of the first convolution layer. And now in this case, I told the neural network train 8 different filters. So it now has 8 different columns here. And each one, again, has a channel. So it will now look for these filters in those images over here. And will tell me in this image where this kind of pattern is present in this already abstract meaning. So you see that from layer to layer to layer, it becomes more abstract what the output means. And if you have pooling layers in between, you scale on the resolution, which means the filters, relatively speaking, are bigger, which means then you look for larger scale patterns. So the last point I want to make is, again, here in the image that I'm showing here, all these filters are colorful, but if you're trying to figure out what this filter actually represents, that's going to be really hard. You're going to stare at lots and lots of those. Quite often you have 32 filters, and if you had like 16 channels come out of the last one, you're staying at 32 times 16 of those little images. It's really hard to figure out what they are, what they do, I should say. And so we usually don't look at the filters themselves, but instead we look at the gray images over here, the intermediate ones. And that's what you will see in the slides that follow that Ryan has. But just remember that he uses a different color scale. So for him now, you won't see the filters. So all of this will go away. What you will see are the gray things, but they're going to be colored now. And that's here. And with that, I will turn it back over. And it's again, the note at the top here, the neuron activations are in color. So these ones, for example, that's what was shown in the gray over here. So the gray over here, the activation patterns now correspond to this. And with that, I will turn it back over to Ryan and stop sharing my screen. And maybe, are there any questions at this point? Does it all make sense? Because this is really important to kind of get the internals of how they work. So if there are any questions, feel free to ask.
There was one question in the chat, Imme, that I answered it in the chat, but I think it bears repeating just for the rest of the class, because I forgot to talk about it in these slides. So Chandra asked, how are the filter weights, the weights inside the convolutional filters, how are they learned? And the answer is that the weights inside these filters, so for example, what's being visualized here in the red-blue color scheme, these weights are learned during training via gradient descent. So it's the same procedure that happens in fully connected neural networks, where you use gradient descent to update the weights inside the neural network, and the weights are updated in a way that minimizes the loss function on your training data. And that loss function, if you have a regression problem, is typically mean squared error, and if you have a classification problem, it's typically cross entropy. So these filter weights are all initialized randomly to small positive and negative values, and then throughout the training procedure, there's an iterative procedure that happens where each example is fed to the neural net a whole bunch of times, and every single time an example is fed to the neural network, gradient descent is used to update the weights in these filters in a way that minimizes the loss function.
One thing that maybe helps to think about too is you can look at convolutional neural networks as being a special case of fully connected neural networks, because what you've basically done is you cut down lots of connections so that there are only a few connections left. And then you also couple some of them because you apply the same filters throughout the same image. So just imagine you cut down on lots of the connections in the fully connected neural network. And then you also constrain certain weights to be the same between different connections. That's what a convolutional neural network is. And that's why all the gradient descent procedures that we talked about last time for a fully connected neural network work right away for this one and are actually much more efficient because you have fewer parameters to learn.
Yeah, thanks, Imme. All right, so the main point of these next two slides isn't really to show people the neuron activation patterns or feature maps, if you will, because as Imme said, these neuron activation patterns, what you're seeing in panels C through F here, are they're sort of difficult to interpret. It's hard to look at one of these feature maps and say, oh, this feature map is picking up on rotational wind, and this one is picking up on convergence, and this one is picking up on low-level weak echo regions or something like that. It's hard to really assign a semantic meaning to each one of these feature maps. So the main point of showing you this image is just to show you what a typical CNN architecture looks like, or maybe not typical, but at least a CNN architecture that's been used in practice. So this is for a tornado paper that I published earlier this year. This is the final model that I ended up using. So the prediction task here was to take a storm, and my inputs were a storm-centered radar image, which is what you're seeing in panels A and B, and then also a proximity sounding, so a sounding from the RAP model for a point near the storm, which I'm not showing in this flow chart just because I wanted to keep things simple. But the inputs were a storm-centered radar image and a proximity sounding, and then the output was probability that this storm will produce a tornado in the next hour. So this is a binary classification task. So what you're seeing here, I'll walk you along the outside of the figure because it's the outside of the figure that shows the architecture of the CNN or the setup of the layers. So the input is, it's on a grid, as you can see in panels A and B. The grid is 128 rows by 128 columns, and there's 14 maps in this grid. So the first 12 maps are just reflectivity at 12 different heights, which are 1, 2, 3, up to 12 kilometers above ground level. And then the 13th map is low-level azimuthal shear, and the 14th map is mid-level azimuthal shear. And azimuthal shear is either as shear as 2 times vorticity or vorticity as 2 times as shear. I can never remember which one, but they're related by a factor of 2. So after the input layer, I have 5 convolution blocks. So not to throw any more jargon at you, but I guess I just did. A convolution block is a number of convolutional layers that are then terminated by a pooling layer. And in this case, each one of my convolution blocks only has 1 convolutional layer. So they're really simple convolution blocks. So I have 5 convolution blocks that are just 1 convolution layer each. So it goes convolution pooling, convolution pooling, convolution pooling, convolution pooling, convolution pooling. And you'll note with the dimensions that as I go through these convolutional and pooling layers, I'm successively doubling the number of feature maps or the number of channels, and I'm successively cutting in half the number of grid cells. So I'm cutting in half the resolution of the grid, or doubling the grid spacing, if you will. So these input images are at a grid spacing of 375 meters or 0.375 kilometers. After the first max pooling, my spatial resolution is 0.75 kilometers. After the second, it's 1.5 kilometers. After the third, it's 3 kilometers. And then 6 kilometers, and then the final resolution after the last max pooling is 12 kilometers. So that allows these convolutional layers that come early in the CNN to learn fine scale features at the finer grid resolution, and then the convolutional layers that are deeper in the CNN are learning larger scale features on a larger grid resolution. So finally, after I've done all of that, I flatten the feature maps that come out of this last max pooling layer. So the where I get this number 4096 from for 4096 features is I just take these 256 feature maps, and they're all 4 by 4 in terms of spatial dimensions, and 256 times 4 times 4 is 4096. So I've just taken these 256 feature maps and vectorized them, so I've flattened them into a one-dimensional vector. And also here I take the features that are detected in the proximity sounding that I told you about earlier that I'm not showing, and I concatenate those 700 some odd features to these first 4096, and that gets me 4864. So what you're not seeing here is there's a separate sequence of convolutional and pooling layers that are going through the proximity sounding, and they're detecting spatial features in the sounding. The only difference between these layers and the ones that are going over the sounding is these layers are doing 2-dimensional convolution and pooling because the radar images are 2D, whereas the proximity sounding is only 1D because it's just a vertical profile. So those convolution and pooling layers are doing 1D convolution and pooling. And then at the end, I have these features that have been detected by all the convolution and pooling layers looking at both the radar image and the proximity sounding. And there's just 2 dense or fully connected layers at the end that transform these 4,800 some odd features into 70 intermediate features, and then finally those 70 intermediate features are transformed into 1 probability, and that's the probability of there being a tornado in the next hour. So that's the final output. Imme?
Yeah, could I just jump in? I just wanted to point out that convolutions, so what's shown on these different blocks, when you look, for example, at the first convolution block, it says 128 rows times 128 columns times 60 maps. That's the output of the convolution. The convolution itself is a 3 by 3 mask. So usually you have, the most common one is a 3 by 3 mask for convolution and a 2 by 2 for max pooling. And we didn't go over this, but the reason is that if you were doing a 5x5 or 7x7, it gets computationally more complex than if you have several 3x3 behind it, one after the other. So if you want to have like a 7x7, you're better off having a few 3x3 sequentially rather than one. But I just want to make sure that it's clear that this convolution, whatever it says over here, is the output size of each layer rather than the dimensions of that layer, just to be clear.
Yeah, thanks, Imme. And I use the same choices in the CNN I'm showing here. So all the convolutional filters are 3x3, and the pooling is all 2x2. So it doubles the grid spacing every time. Whereas if I did 4x4 pooling, for example, I would be quadrupling the grid spacing every time. But generally, people just do 2x2 pooling and 3x3 convolution. Here is another example, again, something that I used for a recent paper. So something that was very much a practical application. In this case, instead of tornado prediction, I was doing front detection. So panels A and B are showing the predictors that go into the CNN. The size of the grid is 33 by 33 in this case, so 33 rows by 33 columns. The predictors at the surface are temperature, humidity, U wind, and V wind. Although, because I didn't want to show 4 different fields on the same map, instead of plotting temperature and humidity at the same time, I'm just plotting wet bulb potential temperature. So that's what the color scheme is in the background, and then the gray wind barbs on top are obviously, well, they're wind. So panel A is showing the predictors at the surface, panel B is showing the predictors at 850 millibars, and then these the circles and triangles are showing the correct answers, which in this case come from human forecasters at the WPC. So the dark blue circles are warm front, and then the light blue triangles are a cold front. So the prediction task is predicting the type of front that exists at the center of this grid. And there's 3 possible answers because I didn't consider stationary or occluded fronts. I considered only warm and cold. So the 3 possible answers are warm front, cold front, and no front. So that means this problem is 3-class classification or multi-class classification as opposed to binary. So in this case, I did an experiment with a bunch of different CNN architectures, and I found that things worked better, as in I got better predictions if I used convolution blocks that have 2 convolutional layers followed by a pooling and 2 convolution blocks in the net. So my first convolution block goes convolution pooling. The next convolution block also goes convolution pooling. And you'll notice again that as I go through the CNN, as I go deeper and deeper, the number of rows in the grid decreases because of these max pooling operations, and the number of feature maps increases. And that's just sequentially doubling the number of feature maps is just a rule of thumb, quote unquote. So it's something that most people do. So after you've chosen the number of feature maps that come out of your first convolution layer, you typically double that number of feature maps with each successive convolutional layer, or in my case, each successive convolution block. So I've gone from 36 to 72 here, and from the first to the second convolution block. There's no great reason that you have to keep doubling the number of feature maps. You could increase it by a factor of 1.5 or a factor of 3. You'd probably get similar performance in terms of how good your predictions are. So after this last max pooling layer, I take all the feature maps that come out of that layer. So 8 times 8 times 72 is 4,608. So I flatten all those feature maps, or I vectorize them into a one-dimensional vector that just has 4,608 numbers. And then I feed those 4,608 numbers or features through 3 dense layers at the end. Those dense layers transform the 4,600 some odd features into intermediate representations with 399 and then 35 and then 3 at the end. And the 3 features that come out of the final dense layer are my 3 class probabilities of warm front, no front, and cold front. And the activation function I use is softmax to make sure all these probabilities are positive and that the 3 probabilities sum up to 1. And I'm going to skip over this slide in the interest of time so that we can talk about interpretation methods. So the first couple interpretation methods, like I said, are the permutation test and saliency maps, which you saw in lecture 4. So I'm not going to rigorously describe the 2 methods again. I'm mostly just going to discuss the difference between applying these methods to fully connected neural nets versus convolutional neural nets, and then I'll show you some results from the CoLab notebook, and then we'll talk about the other 2 interpretation methods, which are specific to CNNs. So in lecture 4, we use the permutation test to interpret FNNs, or fully connected neural networks. And recall that the permutation test quantifies the overall importance of each predictor variable. So in lecture 4, we had 41 predictor variables, and we got a number, we got a ranking over those 41 predictor variables, of which was most important through to the least important. And in lecture 4, obviously the predictors were tabular or scalar features, so there was only one way to permute those predictor variables over all the examples. But in this case, the predictors are gridded or multidimensional, so there's many different ways you could permute the predictor variables when you have gridded data. So the way we do it is that we permute gridded maps over examples. So we take, in this case, we have 4 input channels to the CNN. The 4 input channels being temperature, reflectivity, U wind, and V wind, because those are the 4 variables that we have inside the storm. So when we do the permutation test, we take one of those spatial maps and we leave it completely intact. So we don't shuffle anything in space. We just take a fully intact spatial map, but then we assign it to the wrong example. So let's say that we're permuting temperature. We'll take all the spatial maps of temperature. We leave the spatial maps intact. We don't mess with space. So we don't shuffle anything in space. We just take those intact temperature maps, but then we shuffle them over all the examples. So each example will have the correct reflectivity map, the correct U wind map, and the correct V wind map, but an incorrect temperature map, because it'll be a temperature map that actually comes from a different storm. So the next few slides are the same as you saw in lecture 4, except all I've done is replace the word predictor with the word channel. And I'm not going to go through these slides in real time because you've already seen this stuff. But in case you want to go back later, just if you really want to let it sink in how the permutation test for CNNs is different than for fully connected neural nets, you can go through these slides again. But I assure you, the only word that's changed here is I've gone from predictor to channel. All right, so here you're seeing results from the CoLab notebook. This is the CoLab notebook for lecture 5, where we're using CNNs instead of fully connected neural nets. So again, the input to the CNN for each storm is 4 grids. The grids are all 32 by 32 in space, and the grids contain reflectivity, temperature, U wind, and V wind. So in each one of these panels, the most important predictor variable is at the top, and the least important predictor variable is at the bottom. Or I should say channel to remain consistent with my terminology. And the orange error bars are showing a 95% confidence interval. So where these error bars don't overlap, you can be pretty sure that the difference between 2 channels is statistically significant. So for example, if you're looking at the single pass forward test and you're looking at the top 2 bars, you can be pretty sure that reflectivity is significantly more important than temperature, and temperature is significantly more important than V wind, but V wind is probably not significantly more important than U wind. If you look at the outputs from the 4 different versions of the permutation test, so recall there's the single pass forward test, the multi-pass forward test, the single pass backwards test, and the multi-pass backwards test. 3 of the 4 versions of the test agree on the exact ranking of predictors. So 3 of the 4 versions of the test agree that reflectivity is most important, followed by temperature, followed by V wind, followed by U wind. The multi-pass forward test is a little bit different because it ranks reflectivity first, but then V wind second and temperature third. So it flips the rankings of temperature and V wind. I haven't had enough chance to look into why that occurs, but I imagine that it has something to do with the correlation structure of the predictor variables. So there's probably some correlation that causes V wind to appear as the most important predictor after you've already shuffled reflectivity. So the next interpretation method is Saliency Maps, which again, you've seen this in action for fully connected neural nets, so I'm not going to spend too much time on it here. But just to refresh your memory, saliency is defined by this equation here. So this is the same equation as you saw in lecture 4. There's just a little bit of a difference in this case. So the derivative here is di-p di-x, where P is the activation of the output neuron. In general, you can create a saliency map for any neuron in the neural network, whether it be a fully connected neural net or a CNN. So this activation in the numerator could just be it could be one of the neuron activations from one of the convolutional layers inside the net. But often that looking at saliency maps for hidden neurons doesn't give you useful information. That's not always true, but in my case, I found it most useful to look at the activation of the output neuron. And in this case, for the CoLab notebook, the activation of the output neuron is the final forecast probability. So it's the probability that the storm will develop strong rotation. And then the x in the denominator is one predictor variable. And this weird notation on the right-hand side is telling you that saliency is a linear approximation to this derivative, linearized around the value x equals x naught, where x naught is the value of x in a real example or a real storm. So both here and in lecture 4 for fully connected neural nets, there's one saliency value for each scalar predictor. And you'll recall that in lecture 4, because all the predictors were scalar, we only had tabular data. There were 41 different tabular predictor variables. So we got 41 different saliency values in lecture 4. There was one saliency value for each tabular predictor. But in this case, our predictors come on grids. So we have a 32 by 32 grid, and we've got 4 different channels. So if you multiply 32 by 32 by 4, there's 4,096 scalar predictor variables for this CNN. So when we compute saliency for a storm, we get back 4,096 saliency values. And because the input data are gridded, and we're getting one saliency value for each channel at each grid cell, we can plot the output of saliency as a map on the same grid as the input data. So here I'm showing you the results of that. I'll walk you through this figure because I understand that there's a lot going on. So what you're seeing is the average saliency map for the best hits, and again, this is from the CoLab notebook. So you'll see code on how to do this later. When I say the best hits, I mean the 100 strongly rotating storms with the highest CNN probabilities. So these are the 100 positive cases that the CNN does the best job with. I think its average probability for these 100 storms was 98% or 99%. So it really nailed the fact that these storms end up developing strong rotation. So in the background color fields, you're seeing the storms themselves, and I'm just plotting a composite or an average over the 100 storms. So you can see the composite reflectivity field, the composite temperature field, the composite U wind, and the composite V wind. And then the line contours on the top are showing you the composited saliency map. So the solid contours show you where saliency is positive. That means probability of strong rotation increases with the predictor value underneath. So in this area of the reflectivity core where you have positive saliency values, that means if you increase reflectivity underneath, the probability of strong future rotation will increase. And where you see dashed contours, that means saliency is negative. So that means if you decrease reflectivity here, the probability of strong future rotation will increase. So there's just a few high-level relationships in this map that I want to point out. So this saliency map indicates that the following tweaks would increase the probability of strong rotation for these 100 storms. One is increasing the reflectivity inside the core, where you see these really dark or these really strongly positive saliency values. Also, if you increase the temperature contrast near the reflectivity core, you'd increase the probability of strong future rotation. And you can see that with this dipole or tripole pattern in around the reflectivity core, where there's there's sort of an enhanced temperature gradient here, which may be related to cold pools. So it's saying if you decrease temperature in this area and then increase temperature in this area just to the southeast, you would increase the probability of strong rotation developing in the future. And finally, if you increase convergence and rotation near the center of the grid, you increase the probability of strong future rotation, which makes sense. If you increase rotation now, you increase the probability that the storm will be strongly rotating in the future. And you can see that with the dipole and tripole patterns in the middle of the grid. So it's telling you want to increase U wind here and then decrease U wind here. When you increase U wind, that means you create a stronger westerly, and when you decrease U wind, you create a stronger easterly. And you can see a dipole pattern in this V wind map as well. This next slide is showing you the exact same thing, except in this case for the worst misses instead of the best hits. The worst misses are the 100 strongly rotating storms that have the lowest CNN probabilities. So the worst misses are the 100 storms that end up developing strong rotation that the CNN did the poorest job with. In this case, I think the average forecast probability was 8% or 7% or something like that. So it really missed the fact that these storms are going to develop strong rotation in the future. And the main relationships that the saliency maps are pointing out are that to increase the probability of strong rotation for these storms, You want to increase reflectivity in the core, where you see these dark solid contours. You want to increase temperature in the reflectivity core, where again you see these dark solid contours. And you want to increase convergence and rotation near the center of the grid, where you see these dipole patterns. So it's saying where these solid contours are, you want to make the U wind more westerly, and then just to the east of it, you want to make the U wind more easterly. So you want to drive the winds into each other. You want to create convergence. And if you stare at this pattern long enough between the U and V wind fields, you can maybe convince yourself that the saliency maps are telling you to increase rotation as well. And you see a similar dipole pattern in the V wind map, where you want to create more southerly winds here, and then just to the north of that, you want to create more northerly winds. So again, driving things together, creating stronger convergence, creating a stronger updraft. And I'll skip past the next slide in the interest of time so that we can start talking about class activation maps. So this is the third interpretation method out of the four. And just to review, so as I said in the previous lecture on fully connected neural nets, the permutation test, the first interpretation method we looked at, is model agnostic, so you can use it for absolutely any machine learning model. Whereas saliency maps can be used for any machine learning model that has that uses gradient descent in its training. So linear regression, logistic regression, and any type of neural net you can use saliency maps for. However, class activation maps are less general. They can only be used for CNNs that do classification. They can't be used for CNNs that do regression. Well, they can, but they'll give you some nonsensical output, and we'll talk about that at the end briefly. So I'm not going to define class activation maps mathematically, although I do that in the CoLab notebook. So if you're really curious about seeing the mathematical definition for class activation maps, it's kind of a big nasty equation that has a bunch of summations. So I didn't feel like putting it in here. So I'll define it conceptually instead. Class activation is just the amount of evidence for a particular class, and it's defined at each grid point. So in the CoLab notebook, we're considering only the positive class, which is strong future rotation, although in principle, you could create class activation maps for the negative class as well. So you could find where there's evidence of strong future rotation not occurring. The original class activation mapping method, or the original CAM method, works only for CNNs that end with a global max pooling layer, which is something that we haven't covered in this course because in my experience, I don't think I've ever seen a CNN that ends with a global max pooling layer. So this original algorithm only worked for a very particular type of CNN. So for that reason, we use a different algorithm, which is called gradient-weighted class activation maps, or GradCam. It comes from this paper by Selvaraju et al. In 2017, and it's much more general. You can apply it to most CNNs that do classification. So this little table at the bottom tells you the difference between saliency and class activation. I think this is worth going over because it's really important for how you interpret these maps. So saliency, like I said, gives you one value for each scalar predictor, or for each channel at each grid point. So if you go back and look at these saliency maps, you'll notice that the line contours on top are different for each channel. There's a saliency map for reflectivity, there's one for temperature, there's one for U wind, and there's one for V wind. Whereas the class activation map only gives you one value per grid point. So if I flip ahead one, you'll notice that the line contours on top of each channel are the same. Saliency can be positive or negative, whereas class activation can't be negative. It can be only positive or zero. Saliency, this I think is the key difference between the two methods. Saliency highlights the most important values for changing the model's prediction, because saliency is defined by that derivative dp dx. So it's the gradient of the CNN's output with respect to each predictor, whereas class activation highlights the most important values for yielding the model's actual prediction. So saliency tells you how to change the prediction the model actually made, whereas class activation tells you how to get to the prediction the model actually made. And the last thing is that saliency is not layer specific. So there's only one way to compute saliency. Once you've decided what neuron activation is in the numerator of that derivative, there's only one way to compute saliency. Whereas class activation is specific to one convolutional layer. So in the case of the CoLab notebook, I think there's 3 convolutional layers, so you could create a class activation map for the first conv layer, or the second conv layer, or the third conv layer. And the ones that I'm going to show you in the next few slides, the class activation map always comes from the third convolutional layer, which is the deepest one. So on the right-hand side here, you're seeing the average class activation map for the best hits. So again, these are the 100 storms that actually develop strong rotation and that are the best predicted. So the average CNN probability for them is 98 or 99%. And you'll notice that there's no dashed contours here. There's only solid contours because there's no negative values, because class activation can't be negative. So the darker contours are just telling you where you have higher class activation or more evidence of strong rotation in the future. And in areas that aren't enclosed by a contour at all, that means the class activation is 0 or really, really close to 0. And again, the class activation map or the set of line contours is the same no matter which predictor variable you're looking at. I just wanted to overlay the line contours on all 4 of the predictor variables because there's some people who might want to look at the panel with reflectivity, whereas some might want to look at the panel with temperature, U wind or V wind. So you can look at whichever panel you find the most informative. But you'll notice that class activation map is maximized in a part of the storm that has 2 really important features. One is high reflectivity, and the other is strong rotation and convergence. So if you look at the part of the storm that's inside the darkest contour corresponding to the highest class activation, there's a shift in the U wind field from positive to negative, and there's a shift in the V wind field from positive to negative. So in the part of the storm that likely has the greatest overlap of convergence and rotation with high reflectivity, that's the part of the storm that the CNN sees as being most important or containing the most evidence for strong future rotation. So to me, the pattern that was detected by the CNN here also makes sense intuitively, which is a good thing to see. Here we're looking at the average class activation map for the worst misses. So these are the 100 storms that develop strong future rotation, but that have the lowest forecast probabilities. So the CNN did a poor job with these storms. Again, darker contours show you where you have higher class activation. And again, class activation is maximized in an area that has some overlap between strong reflectivity values and rotation/convergence in the wind fields. So if you look inside the darkest contour corresponding to the highest class activation, there's a shift in the U wind field, not so much a shift in the V wind field, and there is some strong reflectivity inside this contour because it's capturing part of the reflectivity core. Another thing to notice is if you look at the caption in the title here, the class activation is much lower for the worst misses than it is for the best hits. The maximum class activation in this map is about 110, and the maximum class activation in this map is about 4.8. And then, oh, I put the wrong figure on this slide. Well, I guess that's a good reason to skip it. How are we doing for time, Imme?
I was just going to say we need to speed it up a little.
Okay. I can, yeah, I can probably do backwards optimization in a couple minutes. And then we'll go to your last slide, Imme, because I know there were a couple of words that you wanted to say on interpretation methods. So backwards optimization is the last interpretation method we're going to talk about. It skipping over all the mathematical details here. Backwards optimization creates a synthetic input that either minimizes or maximizes the activation of a given neuron. And again, the given neuron can be a hidden neuron anywhere inside the CNN. So it can be just a random neuron from one of the convolutional layers. Although in the CoLab notebook, we focus on the output neuron, and the activation of the output neuron is probability of strong future rotation. So we're creating synthetic storms that either minimize or maximize the probability of strong future rotation. And this whole backwards optimization procedure is done by gradient descent. It's basically the reverse of the training procedure. So during the training of a CNN, you're using gradient descent to tweak the filter weights in a way that minimizes the loss function, whereas during backwards optimization, the CNN has already been trained. You're not playing with the filter weights anymore. Those have been completely frozen, and now you're using gradient descent to adjust the input or adjust the storm in a way that either minimizes or maximizes the probability of strong rotation. So during backwards optimization, you're taking an input, you're taking a set of predictors, and then you're tweaking that set of predictors to give you the answer that you want. This slide talks about loss functions, and it's not super interesting. So in the interest of time, I'm going to skip over it, and I'm just going to show you the results. So in this figure here, I use backwards optimization to increase the probability of strong rotation for a random storm. So this was just a storm I picked out of the testing set. I believe I just used a random number generator, and I picked the storm. And I saw that the for the original storm, which you can see on the left-hand side, so if you split this slide down the middle, on the left-hand side, you're seeing the original storm, which is a pretty innocuous-looking storm. It doesn't have a big, strong reflectivity core. It has a really weak wind field. There's nothing that screams this is going to be a strong storm. So the CNN predicted a strong rotation probability of only 2.64% for this storm. So I used backwards optimization to tweak the storm in a way that would maximize the probability of strong future rotation. And so that's what you're seeing on the right-hand side. This is the synthetic storm after backwards optimization. And for this synthetic storm, the CNN predicted a probability of 99.4%. But to my mind, that's not really justified. You can see some, especially in the reflectivity field, you can see some obvious differences between the original storm and the synthetic storm. So in the synthetic storm, we have the CNN has chosen to create a stronger reflectivity core in this area where I'm mousing around, and it's also chosen to create a convergent and rotational wind field around this makeshift reflectivity core. But the amount of change in this storm, to my mind, doesn't justify increasing the probability all the way up to 99+%. So backwards optimization often gives you silly output, and that was really the one lesson that I wanted everyone to take home about backwards optimization and about interpretation methods in general. You have to be careful with them, but especially with backwards optimization or anything where you're creating synthetic weather data, creating a fake storm or a fake low pressure system or a fake hurricane or whatever it may be. So in this case, I took a really, really strong storm on the left-hand side and used backwards optimization to decrease the probability of strong rotation. So this is what the CNN saw fit to do to decrease the probability of strong future rotation, which to my mind makes sense. I think this change justifies decreasing the probability from 100% to 2.79%, which is what the final probability ended up being, because the CNN kind of tore apart the reflectivity core. It didn't do a whole lot to the wind field surrounding the reflectivity core, but it really turned the reflectivity core into Swiss cheese. But at the same time, this storm doesn't look very physically realistic. And you see a checkerboard pattern or high frequency noise, as it's called. This high frequency noise can be remediated by adding smoothing layers to the CNN and doing a bunch of other fancy tricks. But in general, it's really difficult to make backwards optimization produce fully realistic data. In general, backwards optimization produces adversarial examples, so it produces images that trick the CNN into making a bad prediction. And that was especially what you saw on this slide, where for the synthetic storm, the CNN very bewilderingly predicts a 99% probability of strong future rotation for this pretty junky looking storm. Some work has been done to improve this and make backwards optimization produce more realistic synthetic data. And you can see this paper by Ola et al. In 2017, but that's a little beyond the scope of this course. And then I have this GIF that just shows you backwards optimization proceeding through 200 iterations. This is a case where I made backwards optimization produce a storm that was kind of physically realistic. And I don't know if there's much to glean from looking at this animation other than it's kind of mesmerizing. So I'll go to the next slide and I'll let Imme talk through that slide.
All right, let's see whether I can cover that in 60 seconds. So I wanted to make 4 points here. Number one, just a little warning, not every visualization method is applicable to every network type. And your algorithm, if you're using a standard algorithm, it's not going to tell you. So you kind of have to make sure, it's your job to make sure that the method actually works. So for example, the class activation maps only work if you have, or should only work if you have a fully connected layer somewhere. But even if you throw in a network that doesn't, like an image-to-image sensation network, it's not going to tell you. It's just going to give you some nonsense, which might even look reasonable, but it doesn't make any sense. So it's the key warning is just make sure that you have just a very basic understanding of how the method works and whether it's actually meaningful for the algorithm that you're looking at, for the networks that you're looking at. Number two, we only showed you a few visualization methods here. There are lots of other ones. I listed just layer-wise relevance, propagation line, occlusion methods, there's smooth squared, deconflat. There are lots and lots of those, and there are just 2 packages down here that I use a lot, but that's a question of taste. But I just want you to know that there are lots more out there. The ones that Ryan showed you are probably the ones that are most common in our methodology. I really like layer-wise relevance propagation too, but we won't go into that today. Point number 3, that you are even seeing this kind of interpretation methods is kind of unusual. And that's probably because those are, yeah, and why don't you go to the next slide? with the references, because both the group where Ryan did his PhD, Amy McGovern's group, and my group, we're both focusing very much on interpretability. So we care a lot about these visualization methods. And if you only read 2 papers, I would suggest the one here by Amy McGovern, that's the 4th one. McGovern and Ryan is the 2nd author, making the black box more transparent, because that covers a lot of the method that Ryan was just discussing in more detail. And then our follow-up paper that covers other methods that are not discussed in the paper is the 4th one. So that's by myself and Kyle Hilburn. So if you want to look in a little bit more detail or a little bit slower pace at these methods, I think those 2 are a good selection. Would you agree, Ryan? Okay. So with that, let's go to the Colab notebook. It's high time to do that.
Okay. Oops. Okay. So I'm going to assume everyone has the link to the Colab notebook through either the chat or the group email I sent out earlier this afternoon. If anyone can't get to the Colab notebook, please say something in the chat. So the first thing you're going to do here is, as usual, you want to click on Connect in the top right-hand corner, and then there was, I want to make sure that everyone's running this notebook with a GPU in case we end up having enough time to train our own CNNs. But for some reason, I'm not finding the menu that I usually get at the top of this page. There's usually a file, edit, view, etc., at the top of this page, and it lets you change your runtime type to GPU. Oh, there we go. Okay, there's that. If you're not getting the file, edit, view, etc., at the top, you gotta click on the silly arrow on the top right hand side. And then you want to go to runtime, and you want to go to change runtime type. It's a really good thing I put these step-by-step instructions at the top, because they're I clearly forget things very quickly. And then underneath hardware accelerator, you can choose GPU or TPU. TPU stands for Tensor Processing Unit, and GPU is Graphical Processing Unit. TPU is, I don't know how much better they are than GPUs. If you want to experiment around and try TPUs, feel free to do that. TPUs are something that's completely internal to Google, as far as I know. So they exist only on Google servers, which in this case we're connecting to one. But in general, if you have your own HPC cluster or you have special hardware on your own machine, it's going to be a GPU and not a TPU. So in any case, as we've done before, if you look through the table of contents on the left-hand side, there's some of these code cells that are marked required, and that means you have to run those code cells before you can run anything else in this notebook. So I'm just going to get everyone to go through and click the play button on all the required code cells. So there's cloning the Git repository, importing the packages, just lots of boring housekeeping stuff, preventing auto-scrolling, downloading the input data, and then reading the input data. You may notice that when you get to downloading the input data, it's going to take much longer this time than it did last time, because last time we were only using tabular data. So for each storm, we had 41 different values. Okay, hopefully I can just ignore that message. Yeah, good. So for each storm in the previous lecture, we only had 41 different values, but in this case, we've got 4,096 different values for each storm because we've got gridded data. So the data set is about 100 times larger. So it takes a little while to download, but it should be only a minute or so. So this code cell is probably going to run for quite a while. But as that code cell is running, I'm going to go down to data exploration. This is probably something that I don't need to spend a lot of time going over because you've already seen these maps in the PowerPoint. But this is just showing you what the data look like. So in this case, I'm plotting one random storm out of the data set, and I'm plotting the 4 predictor fields that we have. So we have reflectivity, temperature, U wind, and V wind. And in this case, I've plotted U wind and V wind with wind barbs. And I've put the same set of wind barbs on top of the reflectivity map and on top of the temperature map. So the 2 sets of wind barbs you're seeing here are exactly the same. So this is showing you the 4 predictor variables. And that's for just a completely random storm. And then if you go down to the next item in the table of contents, it's called plot strong example with wind barbs. In this case, I'm taking the strongest storm. This is the one that has the greatest value of future rotation or future vorticity out of the entire validation set. So I'm plotting that storm, so you can see what a really strong storm looks like. And again, I'm plotting reflectivity on the left, temperature on the right, and I'm plotting the wind barbs on top. So you can see this towards in the north center part of the grid. You can see this really strong reflectivity core with values up to 70 dBz, and then you can see really strong rotation and convergence in around that reflectivity core. So the reason this storm develops strong vorticity in the future is probably partly because it already has strong vorticity. I'm going to go back and check on that code cell. Okay, so the input data has been downloaded, and now we're reading the input data, so almost all the required code cells are done. And then we'll just have to run these next two fine normalization parameters and binarization. So I'm going to click play on fine normalization parameters and binarization. And also, you've seen this already as well when I was plotting saliency maps and class activation maps. Instead of plotting the wind fields with wind barbs, because I had other contours to plot on top, I plotted the wind fields as their own separate things. So in this case, I have a 4-panel image where you're seeing reflectivity, temperature, and then in the next 2 panels, you see U wind and V wind. And just to refresh everyone's memory, positive U wind means that it's westerly, so it's blowing left to right, and positive V wind means that it's southerly, so it's blowing from the bottom of the grid towards the top. No matter how much I know that, every time I look at a wind field plotted as a scalar, I always have to remind myself. Okay, so binarization is done. All right. So the one piece of code that I really want to drill into here is the basic example. So this example shows you how to create your own CNN and then train your own CNN and then evaluate it. So the business of creating your own CNN means 2 different things. You have to set up the architecture of the CNN, so you have to determine how many convolutional layers you're going to have, how many pooling layers you're going to have, and exactly how they're going to go together. So how are you going to set up each convolution block? For example, you could have 3 convolution layers followed by a pooling, or you could have only 2 convolution layers followed by a pooling, or you could have 1 convolution layer followed by a pooling and just alternate. There's a lot of different decisions you have to make, a lot of different hyperparameters in setting up the architecture of a CNN. So this is one of the most important parts of doing it yourself, is creating the CNN, determining what the architecture is going to be, and then also determining all the activation functions and the loss function. And in this case, you'll notice that, as usual, I've hidden the nitty-gritty stuff under the hood. So I have you just calling this method that's it's CNN.setupCNN. So the method is called setupCNN, and it's in a file called cnn.py. But in this case, I think it's worth actually showing you the contents of that file so that you can see a little bit about how things are done. So I'll go to the GitHub repository, which everyone should have a link for because I sent that out 1 or 2 weeks ago. But you don't need to follow along with me here. I'm only going to be in this this tab for a couple minutes before I go back to the Colab notebook. So the method is called setupCNN, and you'll notice that it has a whole bunch of input arguments, but to make things easier for everyone, I gave all the input arguments a default. So that's why in the the Colab notebook, you can just call setupCNN with no input arguments, and that will that'll set all the input arguments to their default values. But if you want to play around at home later and train your own CNNs, I think most of the interesting knobs to turn in terms of setting up a CNN are inside here. So you can play around with all these input arguments. You can play around with, for example, the number of convolution blocks. This conv layer channel counts is the conv block layer counts is that's the number of convolutional layers that you want in each block, and this is an array. So if you set this array to, for example, if you make it 3, 2, 1, That'll give you one convolutional block with 3 conv layers, followed by a convolutional block with 2 conv layers, followed by a convolutional block with 1 conv layer. And then the channel counts determines how many feature maps or how many of those neuron activation maps are produced by each convolutional layer. And then there's the dropout rates. So something that I didn't mention in the PowerPoint is that as for fully connected neural nets, convolutional neural nets often use dropout regularization as a way to prevent overfitting. So this input argument allows you to use dropout regularization, and also the last 3 input arguments here are all related to regularization. So there's the L1 weight for L1 regularization, there's the weight for L2 regularization, and then there's batch normalization, which you can either turn on or off. And then there's the filter sizes, which by default I make all the filter sizes 3 by 3. And that's generally the default in the machine learning literature. Although again, if you want to play around, you can make your filters 5 by 5, 7 by 7, whatever you may prefer. And then the next 2 input arguments determine the architecture of the dense layers or fully connected layers. So neuron counts is an array. This just tells the method how many neurons you want in each of your dense layers, and this next argument tells the method which dropout rate you want for each of your dense layers. And then there's the activation function for inner layers. This will end up being the activation function for every convolutional layer and every dense layer except the last. And then outer activation function, or sorry, output activation function. This will end up being the activation function for the final dense layer, which is the one that produces your probability of strong future rotation. So the default here is that the activation function for the output layer is the sigmoid function, because that tends to be the best one for binary classification. But again, if you want to play around and try something different, feel completely free. So if we go inside this method, I'm not going to have a chance to walk you through everything here, but you'll notice that there's a few submethods getting called again and again. So one of these submethods is get 2D conv layer. That creates a convolutional layer that does 2D convolution, so it convolves over 2 dimensions in space. There's get activation layer. That takes in the name of the activation function and also the slope parameter. The slope parameter is only valid if you're doing leaky ReLU. So that slope parameter tells the method how leaky you want your ReLU activation function to be. And then there's get dropout layer, there's get batch normalization layer, and then there's get 2D pooling layer. So this whole block here, which is only 35 or so lines of code, this entire block creates the spatially aware part of your CNN. So it creates the convolutional and pooling layers and strings them all together. And then after this block, you create a flattening layer, and this flattening layer will take all the feature maps produced by the convolutional and pooling layers and vectorize them, or just flatten them into a one-dimensional vector. And then this block of code here creates all the dense layers or fully connected layers that go at the end of the CNN, and these dense layers transform all the features detected by your convolution and pooling layers into that final prediction, which is just the probability of strong future rotation. And the methods that you'll see inside this for loop are get dense layer, and then again get activation layer, get dropout layer, and get batch normalization layer. So these three methods are called for both the convolutional and pooling layers, the activation, dropout, and batch normalization. The only difference between creating the convolutional part of the architecture and the dense part of the architecture, or not the only difference, but one of the main ones, is that in this for loop you're calling get 2D conv layer, and in this for loop you're calling get dense layer at the beginning. And then at the very, very end of this method that creates the CNN and gets it ready for training, you create your model object. So you use this method called keras.models.model. You tell it what the input layer is, you tell it what the output layer is, and then one really important thing you have to do, you can't forget this, is at the very end you have to compile your model. So you do that with this command, model object.compile, and you tell Keras what loss function you want, what optimizer you want, and then what metrics you want. The metrics are values in addition to the loss function that are reported during the training of your CNN. So in this case, I have a constant defined at the top of the file called metric function list, and I'll go find that because, oh, it's in utils.py. Of course, I've grabbed it from another file. The metrics are things like critical success index, probability of detection, false alarm ratio, et cetera, et cetera. So those are things that are reported during training in addition to the actual loss function, which is binary cross entropy. And then the optimizer is something called Atom. We definitely won't have time at any point in this course to get into the different optimizers for gradient descent and what they do. I'll just note that Atom is a pretty standard choice in the literature. All right, so I'll go back to the Colab notebook now, and I'll get everyone to run this code cell. So this is setting up your CNN and getting it ready for training. And you'll notice that when you call setup CNN, you get this flowcharty thing. You saw this flowcharty thing in lecture 4 for fully connected neural nets. So now you're seeing it again for convolutional neural nets. I'm not going to go through every single row of this flowchart and read it all off to you. But basically at the top, you can see input 1 is the name of the input layer. And then you can see that there's a convolutional layer followed by leaky ReLU, which is the activation function, followed by batch normalization. Then there's another convolutional layer, leaky ReLU, batch normalization, and then there's max pooling. So in this case, I've my convolution blocks contain 2 convolutional layers each. So there's one convolutional layer, another convolutional layer, and then the pooling. And for the next block, there's conv2d underscore 2, conv2d underscore 3, and then another pooling layer, et cetera, et cetera. And then at the end, you have this flattening layer that vectorizes everything or turns it into a one-dimensional vector. And then there's a few dense layers that transform everything into a probability. And at the bottom, you can see, again, the total number of parameters inside your CNN and the total number of trainable parameters, or the total number of weights to be learned. So this next code cell down here does the training. So it takes the CNN that we just created the architecture for, and it trains that CNN. So I'll get everyone to click play on this code cell, and hopefully we have enough time to see it do something interesting in real time. So one thing I'll note, while this code cell is running and spitting out a bunch of progress messages, is that the method here is called train model sans generator or without generator. I guess I was being fancy with using French here. But the whole point is that I don't think I've told people what generators are. So what a generator is, and if you end up training CNNs or any type of neural net yourself, generators may be important for you. What a generator does is, instead of reading all the training data into memory at one time, if you have a huge amount of training data, let's say your training data is 5 terabytes or 10 terabytes or something like that, you're never going to find a computer with enough RAM that you can read in 5 or 10 terabytes of data at once, plus all the intermediate data that's going to be created on the fly by the CNN. So if you have just a heinous amount of training data and you don't have enough memory to store it all at once, you can create a generator. And what the generator will do is, you pass the generator to your neural net, to the training method for the neural net, and you specify what the batch size is going to be. So you specify how many examples or how many data points you want in each batch, which might be 1,000 or something. And what the generator will do is you tell it the directory where it's supposed to find all the training data for your CNN. And every time the CNN needs a new batch of examples, the generator will go into that directory. It'll read 1,000 new examples or whatever you've chosen for the batch size. It'll feed those 1,000 examples to the CNN, and then it will erase those 1,000 examples from memory, not from your disk, but from your random access memory, so that you're not bogging down and crashing your computer. So that's the benefit of using a generator. In this case, there's, excuse my scrolling. In this case, there's not so much data that we can't use a generator. So this is why I'm using train model sans generator instead of train model with generator. The input arguments to this method are the model object, the names of the training files, the names of the validation files, the number of examples per batch. There's nothing special about using 1,024 instead of 1,000. Just I've started thinking like a computer scientist in powers of 2 instead of powers of 10. There's the normalization dictionary. This contains the parameters for normalizing the predictor variables. so the means and standard deviations that are used to convert all the predictor variables to z-scores, because that generally works better for training a neural net than using the raw physical values. And then there's the binarization threshold, which is used to define what strong rotation is. I think that ended up being something like 0.005 inverse seconds. There's the number of epochs, or the number of times that I want to present each storm to the model during training, and then there's just the output directory where I want to save the trained model. So if we scroll down through this code cell now, we can see some interesting output. So you can see that we've gone through 6 epochs of training so far. We definitely don't have enough time to get through 100 epochs of training. But after each epoch of training, you'll notice that there's some information Keras prints out for you. So I'll just go through that quickly. There's, first of all, the loss function. So one thing to note is you saw in that CNN.py that I was showing you in the other tab, you saw in my my setup CNN method that I made the loss function binary cross entropy. But actually during training, when Keras reports the loss, if you're using L1 or L2 regularization, you've added those extra terms to the loss function. So what Keras is throwing at you here is the total loss. So this loss that it reports is binary cross entropy plus the L2 penalty that I've added to the CNN. So just be careful when you interpret that. And then there's all the other the metrics that I told the CNN to report. So after each epoch, you can see accuracy, CSI, which is critical success index, frequency bias, which is the number of forecast storms with strong rotation over the number of actual storms with strong rotation. There's POD, which is probability of detection. POFD is probability of false detection. The PERS score is just POD minus POFD. And then there's the success ratio, and FOCN is frequency of correct nulls. So for people who are familiar with contingency tables and know all those scores, that's just what they are. And I know we talked about those in a previous lecture as well. So this is what you'll see during the training of a CNN. Finally, the last code cell that I want to show you, it's this last code cell is evaluating the CNN that we just trained, or the one that we're still in process of training. But thankfully, I still have the output from the last time that I ran this Colab notebook and actually managed to train a CNN for 100 full epochs. So if you look at the code in this cell, it's very similar to the evaluation code that we used for fully connected neural nets. The vast majority of the methods here are the same. So we determine what the correct answers are for the training data, we get the forecast probabilities for the training data, and then evaluate the CNN on training data, and then we do the exact same thing for validation data. And if you scroll down to the output for this code cell, you can see the graphics that we're used to seeing. So you get a ROC curve performance diagram and attributes diagram for the training data, and then you get the same for the validation data. And if you go back and compare to the fully connected neural nets in lecture 4, the all 3 graphics that you're seeing here for CNNs are better than the ones that we got for fully connected neural nets.
So Ryan,
yeah.
there were a few questions in the chat. Apparently, lots of people had their system crash at epoch 29, running out of RAM for some reason.
Oh,
I don't know whether you've seen that. Okay. And then I think we should wrap it up. And I would love for you to give people just 1-minute overview of what you think they should be doing with those notebooks between now. I mean, next time we won't be building much on this, but if on your own, how would you recommend that people use this?
Right. I think the most interesting thing to do with this notebook, if you want to do your own exercises at home, is go through the basic example. So I'm seeing a lot of comments in the chat that that people's notebooks crashed, and it looks like mine may be on the verge of crashing too, because I'm using a lot of the available RAM. So if that happens, you may want to just reduce the size of the training set. Instead of having it be all 76,000 examples, maybe cut it in half or something like that, just to make sure that you're not running out of RAM here. But yeah, I think the most interesting things to play with in this notebook are the basic examples. So I would try tweaking the input arguments to set up CNN so that you can create CNNs with different architectures, different activation functions. Maybe you want to use a different loss function. there's all kinds of things you can do because, as I showed you, there's something like 15 different input arguments to this method. So there's lots of things you can do here, lots of experiments that you could run. Also, you probably don't need to train for a whole 100 epochs if you want to make things run faster. I'd probably just cut things off at 15 or 20. That'll give you close to the best performance. And then I would also go to this this training part of the notebook, and I would try. Well, there's not a whole lot of input arguments to tweak here. Model object is always going to be the model object that you created. Training files are going to be the same. Validation files are going to be the same. You can try playing with the number of examples per batch, so you can see how performance improves or deteriorates as you increase or decrease the number of examples in each batch. Usually, if you decrease this all the way to 1, performance will be really bad. If you increase it all the way to the size of the full training set, performance will get bad. There's typically a happy medium. You can try different binarization thresholds as well. So the threshold I've chosen makes sure that about 10% of the storms are considered strong rotators and then 90% of the storms aren't. But you could make this threshold higher or lower to make strong rotation be a more rare event or a less rare event. So I think those would be the interesting things to play with. And then if you've created and trained your own CNN, I would recommend running these code cells with the interpretation methods. I don't think I would change anything about the interpretation methods. Some of them have hyperparameters that you might want to play with. But I think probably the most interesting thing to do if you end up training your own CNN would be take the CNN that you just trained and then run it through these interpretation methods and see what you get. See if you get what the similarities are between my interpretation maps and yours, and maybe you can find differences as well. And you know, maybe just look at a few storms and interpret what's going on meteorologically.
With that, I would suggest that we stop the recording, but we can still take questions. So I will stop the recording now.